quickly, try to get through the main ideas. I don't want to take too much time because anyway, there's too much technical details. So I'll try to go through the main ideas. So today, so can I start?
Yeah, please.
Yeah. So if you remember, again, if there are any new guys today, please feel free to stop me and ask questions. No need to wait for any permission. Okay, so we had looked at this is sort of the broad outline. So we want to understand what is the reachability set, and we want to introduce this idea, this continuous subsets of reachability sets, which is one of our main contributions. Then prove various things about these continuous subsets. But at the end of the day, we want to prove that these optimal trajectories for the two-player pursuit evasion game, game of two cars, is CS type only, given that the initial distance between the two players is large enough. And large enough as in we know have some inequality under which this holds. So and then we try to go ahead and prove that these are common tangents, and using that we form this 2x2 matrix game. So let's go ahead and try to see what are these reachability sets first. So Dubin's vehicle, yesterday I explained. So you have the location of the vehicle here pointed this way, and there are these two circles. This is the minimum turning radius circle. So if you want to reach, suppose I give you the time optimal, or same thing as length optimal is the same thing here. So I can tell you, I can ask you the question that I want to go to this point. What is the time optimal or length optimal trajectory? So it turns out that this point, as long as this point is outside this circle, it is of this type CS. So you go along. So if you have a point here, you go like this and you reach this point. You want to come here, you go like this and you come to this point. So this part is a straight line, though I am not drawing it nicely. This part is a straight line. So this is a straight line here, starting from here to here. And this part is part of a circle. So this part here, this part is a circle, part of a circle. So that's why we call it CS type trajectory, circle and straight line. So of course, if you want to go somewhere here, the time optimal trajectories become very complicated, because you might have to go like part of the circle like this, then go straight, then travel along another circle like this, and then only be able to reach this point. So in this process, what is the time optimal path is a difficult question to answer. So of course, like I said last time, a lot of research has gone into this, so I don't want to go into that. But to understand this reachability set, we must understand that at least outside these circles, what is the way to get to these circles? Because I want to reach a point, right? I want to reach a point here. So how do I reach the point here? Like this. I want to get here. How do I reach here? I can go like this. I want to reach here. How do I go here? I can go like this, like this. So, but I am given some particular time, let's say somebody fixes this thing and says that, look, you have 20 seconds. And in 20 seconds, what are all the points that you can reach? Yeah. So of course, in 20 seconds, the first answer that you must give is that in 20 seconds, what are all the points? If somebody asks, of course, I can reach nearby points also and not do anything for, let's say I can reach this point in 3 seconds and not do anything for the rest of the time. So that is okay, because V is allowed to be 0 less than V max. No? So you can stay there. So that is okay. But then what is the last point? What are the boundary points that you can reach? So that will demarcate my reachability sets, right? So if you go straight, you can go up to some point. If you go like this, you can go a little bit less far as compared to this, because some part of the circle you have to traverse, and so on and so forth. So reachability set, if you want to draw, you need to know these optimal trajectories, because these last points, the boundary points of whatever set that we can reach, these boundary points can only be reached by time optimal trajectories, right? So of course, as you start off, this picture will not come about, right? Such a large boundary will not come about. So when you just start, you are like this, and you have these two circles, and suppose somebody gives you a time which is like very less, let's say 1 second. So, and depending on the velocity, your reachability set just might look like this also initially. Yeah. So this part. So this might be your reachability set initially, but as time progresses, it becomes bigger and bigger. And in the end, how does it look like is the question. Okay. So that we want to answer next. So forget about the math. Essentially what it says is that what are all the points starting from some initial condition P naught, what are all the points that I can reach in some time T bar. So like I said, if this T bar is small enough, it looks different. It can look like this. It can look some, very little like this also. So all these things can happen. But if this time T bar is large enough, then the reachability set looks like this. Now, what is this? You need to understand. So this is very important that you understand this for the rest of the lecture. So these two circles, these two small circles are the minimum turning radius circles, left and right. So this is pointed this way. Okay. Now, if you go like this, you reach this point. Go straight ahead, you reach this point. You go like this, you reach this point. You travel further, you reach this point. You travel further, you reach this point. You travel further, you reach this point. But a little bit more, you reach over here, this point. You do not reach this boundary. It's very important that you understand this, okay? Because without this understanding, all the arguments will fall through. So you reach this boundary over here.
Professor Devraj, this
Yes.
has been computed geometrically or computationally, or it's in some closed form? How do this set has been computed?
This particular picture is computational, but we don't use explicit boundary computation of this set for our computation. So
No,
like I
that
said,
you are doing final. See, your solution
yes,
is based on tangent, but this
yes,
is done computationally, right?
this is just done computationally, just for showing. I mean, yeah, this is not efficient or anything. No efficient computation is claimed here. We don't have any closed form solution of these boundaries.
No, I don't think it exists also, because people do have a approximate using Apollonius circle.
Yes, that is true.
Yes.
But for us, it is very important to know, because we are looking for optimal trajectories, but we want to use geometry. These two things together, since we are putting together, for us is very important to understand this inner boundaries and this outside boundaries. So this boundary here, this boundary is different from this boundary here. Why? Because if I had chosen the left circle, I can reach only up to here. I cannot reach this point. This point, if I had chosen the left circle, then this point is unreachable. This is not reachable in the time T bar. Of course, if I allow more time, I will be able to reach those points. But in some time T bar, I cannot reach this point. Okay. So this gives us a very interesting situation. What is the situation? That if, on the other hand, if I had started on the right circle and somebody told me to reach this point, so that is not a problem. In time much less than T bar, I can reach this point. I want to reach here, I start on the right circle, I can reach this very easily. On the other hand, if I had started on the left circle, I cannot even reach this point, because the left circle part, if you take away the left circle part from this figure, I'll draw very roughly. So suppose you start from here. So this one looks something like this. Okay. So these are the two inner circles. So rough drawing of the same figure. I can even shade this one if you want. It looks like this. Now, of course, the question remains that what about these small inner circles? Can I go inside these inner circles or not? Well, it depends on the time. So luckily, we have been able to avoid completely going inside these circles for our computation. So very, what do you call it? We sort of cheat about it by not even trying to go inside these circles. So if you have to go inside these circles, if you allow enough time, it might be that some part of this circle is covered. We can reach, let's say some time T bar is such that I can reach up to here. Maybe some part is left, this empty part is left. That is possible. But we don't worry about it. About the space inside the circles, we can avoid it completely by some tricks further down the line. We'll come to it maybe. But more importantly, outside points over here, these points can be reached. If I start on the left circle like this, but not these points. These points cannot be reached if I start on the left circle. Okay, in time T bar. Of course, these points can be reached if I start on the right circle in time T bar. So, but anyway, reachable set definition wise, this is the definition of the reachable set, and this is how it looks. Okay. So now, since we have this reachable set, so we want capture. So what is the first guess? If I pick out, assuming that none of you guys, except for Professor Kothari, has worked on this problem before, I said that when will capture happen? Yeah. So you will say, okay, reachable set are all the points that one of these Dubin's vehicles can reach. And the evader is also a Dubin's vehicle. The pursuer is also a Dubin's vehicle. So capture should occur. The first guess should be capture should occur when the pursuer's reachable set contains the evader's reachable set, right? So suppose if you look at this left figure, the evader is over here, and we have sketched out this one. So this is the evader's reachable set, and the pursuer's reachable set is this one. So you should say, okay, of course, if there is some area over here which is not covered by the pursuer's reachable set, the evader can go and hide over here, and it will not be captured. So capture should occur when it gets covered, right? So that should be the first guess. So when this sort of a situation happens, this is sort of the capture condition in terms of reachability sets. Okay, so at least this was our first guess. So this one happens to be not true. So here's a very clever counter example, one that we could figure out only after some time. So let's look at this. Yeah, so this figure, I apologize, this is like not about I am claiming that, okay, I'll just make this smaller. So I'm just claiming that this one and this one, these two reachability sets are reachable sets or reachability sets. These are the same. It's just that this is actually generated using some values, and this is just hand drawn using Xfig or something. So just I apologize for the difference, but essentially this is the same thing that you should be able to appreciate. So same thing. This is the two inner circles, this one and this one, and then this is the left reachable set. So this one like this up to here, and this one, this is the left reachable set, and similarly the right reachable set. Right reachable set and left reachable set we call when you start on the left circle first and then go in a straight line. If you start on the right circle first and then go in a straight line, we call it the right reachable set. So this is the situation, and what happens? What is it that we are claiming here? So here is the pursuer and pointed this way, and here is the evader pointed this way. So we are looking for the first time instant when the pursuer's reachable set covers or contains whatever you want, the evader's reachable set. So this is the picture of that situation. So this is the first time instant. Yeah. So let's call it some T1. Yeah. When the reachable set of the pursuer contains the reachable set of the evader. So this is, you can write it mathematically, infimum of the time when this happens. Okay. And this is the picture that we have here. So you can see we have not drawn the evader circles. They will be somewhere here like this. Okay. Is the picture clear? Anyway, there are very few participants. You guys are listening or not? What, Arijit?
Yes, sir.
Can you understand this figure?
Yes, sir.
So you are pointed downwards like this. The evader is pointed here. The pursuer is over here. And what do you think is the optimal trajectory? Arijit, why don't you answer to get some feedback from you guys?
It can take immediate left turn and then follow a straight line to try to capture the evader.
Yes, so that's what is shown here. You turn hard left, as it's called, and then just follow this line and capture over here. And the evader, what it does not go along any circle. It just goes straight, right, and gets captured over here. So in that case, we figured, okay, this is not bad because this is the first time instant when the reachability sets are getting covered. Reachability set of the evader is getting covered by the reachability set of the pursuer. So this is a good play. This is the best that the evader can do. Yeah, because what else can the evader do? Its entire reachability set is getting covered. So it has no other choice but to use this one only. So this is the optimal policy. This is the saddle point strategy of the evader. Yeah. So it turns out that this is not correct. Huh? Why is this not correct? So what it does is that evader, if it does something a little bit more clever. So remember in earlier case, what I said was that the evader starting from here is going like this and hitting this point. And this point is the first time instant. This is the first time instant when the reachability sets are getting contained by the others. So it seemed like it's a good thing, but it's actually stupid of the evader. It should not do this. What it should do is what is shown in this figure. So what it should do is that it should not, so we have these two circles, right? So what it should do is that it should just go along this circle a little bit and go like this. And of course, pursuer will also do the same thing. Pursuer will also take, so these circles are smaller now. It also does this and then comes and catches the evader over here. So it does get captured anyway. That is already guaranteed by our initial assumptions. But once it gets captured over here, the time taken is longer. So the time over here, let's say this is T2, this is greater than T1. So for the evader, it's actually a good idea to not just aim for this point. But on the other hand, this is the point when this T1 was the point when the reachability set containment worked, right? So here the reachability set containment has already, gone long past. It was already contained, and still we have to wait for longer time until some other type of condition is met. And then only the
Devraj,
capture
what is
occurs.
difference? This T1 is just in T1 it is a straight opposite, and T2 it's just slightly right hand side, right?
Right hand side, but you see this is like a longer time, so much before. So if you let this is T1, and if I wait for longer time, this will be the reachability set will grow, right? It will be like this.
Yes.
So it will be like this. And if the evader, instead of going like this, if it had gone like this, the capture would have occurred over here and not over here. It would have occurred over here. And because this is longer time, the capture would have occurred at T2 instead of T1, where T2 is greater than T1. So for the evader, you can postpone the capture by playing this strategy.
Okay, so now I realize that, see, when we look into geometrically, the time is somehow we don't look, but time is evolved.
Yes, the time is evolved, and as the time evolves, the reachability set grows. And so normally speaking, I would have said, when does this game end? This game ends optimally when the reachability sets contain each other, but that is not true. So this is containment of the reachability set is not a sufficient condition for optimal evasion, at least, because the evader can postpone it longer by doing something else, when actually this containment of reachability set has already happened and has, more time has passed. So this was the first hint that we need to look for something more.
Very interesting. This is a very interesting result.
Yes.
Sir, I have one doubt. Is it only one condition it fails, or is there are a lot of conditions for it to get failed?
The containment of the reachability set.
Yeah.
Yeah, some other situations where it will fail, you were saying?
Yeah. Like,
yeah, I'll tell you exactly. We have a complete characterization. From there you can figure out where all it will fail. So we just don't have, we have a solution to this, and it's just not a fix for this one. It's a fix for all such situations. I'll tell, but let me give one more counter example first. Okay. So second case might be that, okay, so this one, it seems like, okay, what is happening here at T2? Only the left reachable set is containing the entire reachable set of the evader, no? So in this picture, so earlier in this picture, let me rub off this. At T1, what was happening was that the reachability set, the entire reachable set of the pursuer was containing the entire reachable set of the evader. So that one failed. So this one failed. But in this picture, capture is happening optimally over here. Now, but what is happening over here in terms of reachability sets? The left reachable set of the pursuer is containing the entire reachable set of the evader. So maybe that is the condition. Maybe we should not look for just containment using reachability sets, but we should concentrate on the left reachable set and right reachable set separately. That was the second case. The second case is that maybe the initial direction matters. Maybe the left and right reachable sets, those are the ones which we should concentrate on. So we look at this left reachable set. I have already drawn it, so I guess I don't need to explain this again. So left reachable set and the right reachable set, the two figures that I have over here, these are maybe we should look for containment using this only. So second case is that maybe initial direction matters, is containment by one of the reachable sets, any one of this, left or right, necessary sufficient condition for optimal capture. That was the second case. Yeah, so the earlier example gives us hope that this is probably correct. But now, after a lot of thought, we could come up with a counter example to this also. So what is happening here? So you see, this one, it was working. The containment by the left reachable set was working. But here, what is happening here is that the evader is over here, and evader has these two circles like this, and the pursuer is over here. Pursuer, two circles are like this. So the optimal path of the evader is to go like this and end up at this point, and the pursuer would be to go like this and end up at this point. This is the optimal capture. So, but here the left reachable set I have drawn over here. Rough drawing, but left reachable set. This is the left reachable set, and this is the right reachable set of the evader. But you can draw the other reachable set also if you want. Yeah. So If you want, you can draw this one also. Doesn't matter. But the left reachable set is not containing the entire reachable set of the evader, but still capture is happening. So optimal capture, but no containment by the left reachable set. So and clearly not, of course, by the right reachable set also. That you can draw and check. So clearly that guess, the second guess is also wrong. That this left reachable set containment by only that reachable set is good enough. That is also not correct. So now there is something big missing over here. So what is that thing? So why does this one fail? Yeah. So let's investigate the first one, and try to understand this. The one of the questions that one of you asked also should be answered now, slowly. So this one, what is happening? You see, this evader is going like this and ending up over here, but it's not optimal. So it's not a good strategy for him. He could have done better. Why? What is he missing? You look from the evader's perspective. What is he missing? He is missing something very important. What is that? That he is looking for this outer boundaries. He's trying to reach this outer boundary as quickly as possible. But that was stupid of him. Why? Because this inner boundary is also important, right? Because the moment this evader starts anywhere, this direction, or he tries to go along these circles anywhere, the pursuer has to take a decision, no, whether to follow the left circle or the right circle. So depending on his decision, the evader, what he can do is that he can quickly see that suppose the pursuer started on this circle like this. In that case, the moment he started on this circle, he cannot cross this line in this given time. So if he comes like this, he will be stuck at this line. He cannot cross this line. So for him to cross this line, he requires more time. So what the evader should have done is that instead of going straight like this to this point, to the outer boundary, he should have tried to reach this boundary first. If he had reached this boundary first, he could have probably bitten the pursuer to this boundary, and he could have extended the time. So this is exactly what happens. So this is some complicated figure, but I'll try to explain. So if you can, this right hand picture is a blow up of this part of the figure. This part of the figure is blown up over here. Okay, so this is the rough drawing of the evader's reachable set, and these are the left reachable set of the pursuer, and this is the right reachable set of the pursuer. Okay, so the pursuer is pointed this way, the evader is pointed this way. So what is happening here is that the evader can take any of these trajectories. So evader can take a trajectory like this, he will get captured here. Evader can take a trajectory like this, he will get captured over here. Because why? Because the moment the evader tries to go like this, the pursuer will just adjust it's a feedback strategy, right? It will adjust and then come over here. If it tries to go like this up to this point, this pursuer will adjust and come over here, no problem. But if the evader goes like this over to Y, the pursuer cannot cross this boundary over here. Why? Because this point Y is in this given time, whatever t bar for which I am drawing this. Of course, if you allow more time, the pictures will change. But at this t bar, this is the boundary of the evader's reachable set. So it can go up to this point Y in this t bar time. But the pursuer cannot, because the pursuer's reachable set is bounded by this one. Yes, it will be stuck here. So what is going to happen is that it can avoid capture for some more time, and the actual capture is going to happen over here, like the way I showed. I mean, maybe it is better to show over here only. So you have a larger time you have to allow, and the evader goes like this and ends up over here, and the pursuer now has enough time to come and catch him over here. So this is what is shown in this figure also. Yeah, this is like blow up of that particular situation that we showed earlier. So what is happening here is that this is the sort of crucial central idea in this entire thing, that capture using feedback strategies will only occur if and only if, in fact we prove later, if and only if evaders all possible variations can be replicated by the pursuer also. So here you see, because we are crossing this line of so-called, let's say, discontinuity, we will define it properly later. Because we are crossing this line, the evader can cross this line. It sort of, really tricks or outwits the pursuer. The pursuer cannot cross this line, so it sort of is saved for some more time. So this is the optimal strategy, and for it to be an optimal strategy, what is going to happen, what is required from both points of view is that whatever variations, so evader can reach here, and let's say we create a curve like this, just an example curve, and evader can go anywhere here. So all these variations that we have over here can or should be, the pursuer should be able to replicate these variations all the way through. But it cannot, right? It cannot cross this point. So as a result of which, we are not satisfying this very important condition that is sort of essential to this capture condition. And that's why capture does not occur over here like the way that we expected earlier in the first guess, but it failed. Okay.
Professor Devraj, so this grid you have shown in the
Grid, yeah.
right-hand side figure. So I guess, do you want to show this through this grid point that this is an area where the evader can reach before pursuer, right? On the for left reachable set.
The evader can, yeah, you are right, but only one thing. So the evader can reach these points, this grid, whatever I shown this grid, the evader can reach these points. The pursuer cannot reach this point in this time t bar for which this picture is drawn. The pursuer cannot reach this once he has started on this left circle. If he had started on this right circle, then the evader strategy should have been, he should have gone the other direction.
And
So-
there is this, and therefore this is like you can see these are the disjoint set, right?
Disjointed, I would not use, but you can use the word safe region because I think that is sort of standard in the literature also.
Yeah. So this safe reachable area is there, that Tomlin and the.
Yes.
So
This is
I
safe
have
reachable. Yes.
one of in my work also computed I safe reachable. I don't know whether you have seen that paper or not.
I think I haven't seen, but I was looking at your lectures in this series only. I think your lecture only I looked at.
Huh.
I think you had something to say about the safe reachable area also, no, in one of these lectures.
Yeah. So safe reachable area, this is the area where evader can reach. So using Dubin's curve for non-holonomic systems, because we can't do this partition like Voronoi partition. So only
Yes.
way we can do is using the this Dubin's set only.
Yes.
And this is where the way you have identified, this is where the evader can maximize its time reaching there.
Yes. So all this computation would have been, of course, very difficult to do, and you have to approximate using various techniques to
And
calculate.
I think our work has sorry for interruption, but our work has that try to approximate. So then it's the algorithms become bad.
No, in many practical situations, you might need to approximate only.
Yeah,
It
because
is only
we have,
under in only under these specific conditions that this computation reduces.
so we have considered equal speed. So in that case, we have to discretize and approximate.
Yes. It is equal speed or asymmetric capabilities. Like one of them has greater speed, the other one can turn faster. For all these things, I think you have to approximate. Otherwise, there is no solution as of now.
Yes, so that's what we have done. We approximate.
Yes.
Equal.
Right.
Sorry, just because see,
No,
we have
it's good
similar.
to have a discussion. Yeah, I like.
Yeah, we have similar things, so we could.
Yes, of course. Okay. So, so this to make this idea concrete, that all possible variations we should be able to replicate. So I am not sure whether there are any math guys over here. So this is very similar to the idea of homotopy, that in algebraic geometry, this is like studied very carefully and whatnot. But anyway, we will not go into that in these lectures. So anyway, so we do it our own way. So continuous subsets. So how do we do it now? So we say we want to define this continuity, this idea of continuity. Continuity in what sense? That as we go along this curve, the pursuer should be able to follow these variations. So this idea we want to mathematically write correctly. So to do this, what we do is that we just look at this very simple idea. We draw. So suppose we want to identify a region of a reachable set which has this property. Yeah, what is the property? That we draw a curve like this. Any curve between any 2 points, or the curve should lie entirely within this set. And this curve, we take any 2 points on this curve, and we try to reach these 2 points starting from the initial condition of pursuer or evader, doesn't matter. This is like a general definition. So if I want to try to reach this point, I should be able to reach like this. Sorry, I should be able to reach along this line like this. If I want to reach this point, I can reach like this. So if I go from this point to this point and I look at the two curves that are required to reach this point, so C1 and C2, suppose this is okay, Z and W. So the question is that is Z minus W in whatever norm you want, let's say 2 norm, as this goes to 0, C1 minus C2 in some appropriate norm, I think we have used the L-infinity norm, does this go to 0 or not? So this is our definition of continuous subsets. So for subsets I have not defined, I have just defined some sort of nature of continuity of these points on this curve. So continuous subsets are what? Is such a subset of the reachable set such that any curve I draw has this property. What is the property? That I take any 2 points nearby and I calculate what are the trajectories required to reach this. So in that case, if these points are nearby, are these curves nearby? So that is our concept of continuity in subsets of reachable sets, and subsets which have this property that all such curves obey this continuity condition are called continuous subsets. So if you go back to this, this picture, which is sort of the heart of the matter, if you go back to this picture, as you can see, as this point over here, this point over here, suppose I take these 2 points, the pursuer trajectories can reach here, the pursuer trajectory can reach here, and if these 2 points are close by, the curves, these 2 curves also are nearby. So these are all good. But let's look at this point and this point. You see, in the given time, if I have to reach this point, I have to come like this. But if I have to reach this point over here, I have to take the right circle and come here like this. So see, these 2 points might be close by, just on 2 sides of this line. But the curves, the C1 and C2, these 2 curves are not nearby. They are very far apart. So there's a discontinuity in this sense. So,
Professor Deva, that's why I was telling discontinuity, because this set are discontinuous for capture point of view.
yes, very correct. Yes.
Because although it's physically they are close, but the way solution does not exist.
Yes. So very small variation over here creates a large discontinuity in the curves required to reach these points.
So just I want to add, because from safe reachable area point of view, it's become like non-convex. Because if you draw the area, there will be hole here, because the variation you do on the boundary, so there will be, because I cannot reach in this what you have grid from the left hand side.
Yes.
So if I committed from the left hand side, I cannot reach on the grid.
Yes. So this is, you can consider this a hole. I mean, the shaded region you can consider like a hole. You cannot go there.
Yes.
That is true. In the given time.
Yes. Time is what important, right?
Yes. Very true. So so this is a lot of math here which we can forget about for the time being. So essentially this is what I was talking about. So if you take 2 nearby points, the curves that reach this point should also be close. Okay. So continuous subset is such that any curve that you draw has this property. So that's essentially the idea of continuous subsets. And here are some examples of continuous subsets. So the left reachable set that I have over here is a continuous subset. The right reachable set is a continuous subset. And this is some special set, which I don't think I'll have time to explain why this is called a blocking set. But blocking is very important. I'll give you a hint because this is very interesting. You see, you start, suppose this is the pursuer and suppose this is the evader. Okay, like this, let's say. So the pursuer will try to do what? It will try to come like this as quickly as possible and try to catch this guy, no? So the evader, it might try to go along this trajectory and it might try to go away, it will get captured. So in some cases, especially if these 2 are not too far away, the best strategy for the evader actually is go and enter this circle. So this is the evader, this is the pursuer. Yeah. So the best strategy for the evader in some cases is to go and enter this circle. In some cases, actually, it's a good strategy because it will not get captured easily. Because once it enters this pursuer circle, the pursuer has to come out and go in like this, na? So that takes a lot of time, and the evader can do something again in that time. So there is some blocking involved. Blocking in the sense that the pursuer always has to be careful that the evader does not come and sit inside its turning radius circle. So in that analysis, this blocking set is important, but how to go into this blocking set. But you can check that this is a continuous subset in our definition. You create any curve over here, you can reach. Essentially, you can look like this. It's easy to draw like this. So any points, all these curves have this continuity, right? And because this area is not there, no chance of drawing the curves like the way I was drawing earlier, which creates this discontinuity. And left reachable sets, right reachable sets, these are also continuous subsets. In fact, you can do a very clever thing and include almost the entire reachable set as a continuous subset if you only exclude this line. If you exclude this line and you say, look, PB is not included in this set, this straight line only, then also you are safe, because you create any straight line here, no problem. You can reach here, you can reach here, you can reach here, you can reach here. But remember, the problem was with these boundaries, no? So these boundaries are excluded because you cannot draw a line across this PB. So I think not enough time to explain fully, but I guess you have to take my word for it, that if you exclude this PB, then this becomes a continuous subset. So why am I showing you this special continuous subset? You could have created many other continuous subsets also. You could have just said, look, this is a continuous subset. That is also true. That's also a continuous subset. I'm showing you this special ones, and I have named them as pursuer continuous subsets and evader continuous subsets. Anyway, there's no meaning to that, right? I mean, continuous subsets are continuous subsets. But I have named them as pursuer evader because these special subsets, these three types over here and this one over here, play a role in the optimal capture. Okay, so that's the let me skip this continuous safe region. Okay, so this is the usual idea of safe region, which I think some of you know. So this idea of normal safe region is modified to have this continuous safe region to include our idea of continuity in these sets. So essentially, it is just the set subtraction should be 0 or not, not 0, but the region that is left is the one set minus the other. But these sets, instead of being just reachable sets, these are continuous subsets of reachable sets. But let me skip this. So in terms of this safe region and continuous safe region, we can define the time now, right? So what is the time? So earlier, this time to capture that we were trying to identify, we said that, look, this is the minimum time or infimum time at which the reachability set of the pursuer contains the reachability set of the evader. Now we change this now using this idea. We say this is the infimum time at this point of time. What happens? For every continuous subset of the reachable set of the evader, there exists at least one continuous subset of the pursuer's reachable set, such that the safe region with respect to these two sets is 0. So this is exactly the picture that you should have in mind. So remember, for the evader, this was a continuous subset. Yeah. Remember, we have to exclude some point over here, line over here, but other than that, this is a continuous subset. And this is the pursuer reachable set continuous subset. And you see there is no safe region. The safe region means what? You just subtract one set from the other, and there is nothing sticking out, nothing like this sticking out. So this usual idea, but in terms of continuous subsets now. So that's all that we do. We introduce this idea of continuous subsets, and this happens to be if and only if condition for capture. So this time, which is just written out, this time just written out as the infimum time at which we have continuous containment. We call this continuous containment. Yeah. So once we have this continuous containment instead of the usual containment, then we have if and only if for capture. So condition for capture, let T be defined as in this is like the continuous containment for a time, infimum time where continuous containment happens. Then for every trajectory of the evader, there exists a pursuer trajectory such that the endpoints match, capture is happening. Yeah. And similarly, the other way around is also true, that T be again defined the same way as the first instant when continuous containment happens. In that situation, for every pursuer trajectory corresponding, pursuer trajectory P, there exists a evader trajectory such that we can avoid the capture until this time t. Okay, so essentially these two theorems together says together that this t, the instant when continuous containment happens, is the min max time to capture. Okay, so this is sort of the one of the main results. So Professor Kothari, listen, I think it's quite late and people are dropping off. Let me quickly wrap up. Huh?
Yes, yes. So I think anyway, you have given the
Yeah.
main idea yesterday only.
Yes.
So unnecessary, for sake of, we will not push it.
Yes, yes. So what I'll do is that so we have